Welcome to Chapter 11. In Chapter 11, we're going to start talking about the statistical inference when it concerns variances. Up until this point, we've taken a look at single sample mean and two sample mean. Now we're going to move to variance, and the real reason we do this is to get into the area called chi-square, and then F. Now F will be when we compare two variances simultaneously, and chi-square will be when we look at one variance. We're going to move on from this ultimately to something called a ANOVA when we look at multiple means simultaneously, but we'll be looking at something called an F statistic, and that's brought up here. So Chapter 11, what we're going to do is talk about the chi-square. We're going to build confidence intervals for the population variance. So we're going to try to build around sigma squared. We'll do hypothesis tests, so we'll always do a creation of a statistic. We'll do a confidence interval and a hypothesis test. Two-tail and both left and right tail. Then we'll move into the F distribution and do the same things. Calculate the statistic, and then do confidence intervals and the hypothesis test for all three as we've seen before. So what is this? Well, what we're going to do is infer about the population variance sigma squared based around a sample S squared. We've seen this many times. The big difference between sigma squared and S squared is that sigma squared does not rely upon degrees of freedom. It would be how we deviate about our mean squared on average as we divide by n. S squared would be the sum of those deviations squared divided by n minus 1. So the chi-square, as we look at it when we make our inference, we're going to call it that big X squared distribution. We often note it as the chi-square, and below that we'll put degrees of freedom along with it, and many times we'll put whatever we will have the alpha level to be. Now for this, we have to create the statistic. Well, since we know that S squared is dependent upon the degrees of freedom as we calculate values, sigma squared is not. If we want to see how well does that variance of the sample relate or ratio to the population variance, we'll take the S squared over the sigma squared and multiply that ratio times the degrees of freedom, n minus 1. So if a sample size of, say, 11, the degrees of freedom would be 10. So when we refer to this, the chi-square, it would be S squared over sigma squared times n minus 1. That statistic, under the right circumstances and assumptions where we have the assumption that data is normally distributed, the chi-square is nothing more than a compounded additive value of a whole bunch of z squareds. So the chi-squared is just an extension of the normal distribution. As we'll see, the F test, since it's based around two chi's or two sample variances, then it too is based around the normal distribution. So how do we do this? Well, the chi-square shape, if you look at it, looks a lot like what we saw before. Except that when we look at chi-square, you'll notice in this picture, if this represents where 0 is, notice there are no negative values. This does represent an asymptote along the vertical axis and the horizontal axis. And you'll also note that as we increase the degrees of freedom, it looks more and more symmetric. So when we go from 5, it's very peaked with a big kick to the right. 10, still peaked with a kick to the right, but not as dramatic as the one at 5. And now when we get to degrees of freedom at 20, it starts to look like a normal distribution. And that will go on and on and on and on and on until we get something that's nearly flat but has a nice symmetric distributional shape to it. So obviously the more degrees of freedom, the easier it is to predict something. I think by now you've caught on to the fact that as we get something to be more and more bell-shaped or mound-shaped, the easier it is to predict, given in the empirical rule allows us to figure out how many are in space for prediction. We want things that are normal. So when we look to the upper tail and lower tail of this distribution that seems to approach that normal shape, to the upper tail, we'll say it's chi-squared, and we'll represent it by alpha and the degrees of freedom. So if I refer to chi-square of 0.05 and 10 degrees of freedom, I'm referring to the upper tail. Now, think back. The z distribution, if you move from left to right, it went from 0 to 100% along this axis. So 0 to 100%. T reversed it. Chi-square is reversing it as well. going from 0 to 100%. So you're essentially flipping around what the shape would look like. So if I'm calculating the right tail, I'm looking at just the alpha level. Normally it would be over here for the z. That's what we're pretty comfortable with. Remember, it's over in the right tail when it's just alpha. So if I had degrees of freedom of 10 and alpha of 5%, I would use a call in Excel called chi-square CHISQ dot inv, so it's a value, and right tail. So the RT represents that. So I throw in the 0.05, the 10, and I get a value of 18.3. You can also back out, if you know the chi-square statistic, you can calculate the probability of where it would fall. So in this case, I plop in the 18.307 and the degrees of freedom, and I use chi-square dist.rt, right tail, and that's how I get my 5% back out. So it'll tell me where, in terms of the space, along the number line looking from right to left, 5% would be where that value 18.307, that's the uppermost 5%. If we look at it directly in Excel, just so you can see it, I would use that calculation. You can see how it would work. And again, if we want to back it out, I can calculate the 5% by putting in the 18.307 and the 10 degrees of freedom. As you can see, we're going to have a lot of examples in this chapter. It's not a difficult chapter, but it is nice to see some problems worked out. So, right tail is easy. Left tail, what we do is, instead of having alpha, it's 1 minus alpha. So if I said alpha was, say, 5%, now in the left tail, I'm going to say 0.95 and 10 degrees of freedom. So you could use the right tail function and put in the 0.95 as it's showing here. You could do chi-square .inv.rt of 0.95. That's actually going to flip it back. Or, while Excel doesn't do this, it's implied that the left tail, CHISQ.inv, nothing after it, chi-square.inv of 0.05 and 10, that gives you the left tail. So to see it, what I'm doing is showing the right tail was just calculated at 5%. That's where we got that 18.307. To calculate the lower tail, the left tail, where is this value of 0.95 and 10, that's 1 minus alpha? All I would do is use chi-square.inv of 0.05 and 10. So if I look at it in space, from the lower value, there's our lower value, and then we look at our upper value of 5%, 18.307. Notice they're both positive. Of course they're positive. The variance is a squared measure, so it has to be positive. And this is just the display of how it would be done. You just saw that in the graph on Excel. And I'll include the Excel sheet for you to look in your module. So now that we're able to calculate a chi-square statistic, let's create the confidence interval for it. Once you see the confidence interval, the variance, the hypothesis tests are pretty easy. So all we're going to do is try to figure out what does it look like to build a measure of confidence around a population variance. Well, the only way we can do this is to start with the sample variance. We're going to use the value of n, the sample size, and its associated degrees of freedom, n minus 1. And the alpha level we use, we're going to cut in half. Half goes in the right tail, half goes in the left tail. Remember, they're reversed. Now, it's pretty easy here, and I'll tell you how. Since the numerators are going to be the same, degrees of freedom times s squared, notice that's the numerator you would normally get when you create a chi-square statistic. Remember, we saw that before. The difference will be the one that's larger is the one that would go here. The one that's smaller would go here. If you just calculated both and didn't know anything else, if you calculated them correctly, picked a larger one, put in the left, you need a smaller value on the left and a larger value on the right for it to be a confidence interval. Just a quick check. Just make sure when you're doing your work, this is what you find. Let's just say that we have a sample size of 10, and we know the sample standard deviation is 37.13. We want to build a 95% confidence interval around the population variance? Well, right off the bat, we have this. It's our sample standard deviation. So we're going to have to square it. We're squaring it here. We're squaring it here. The degrees of freedom is 10 minus 1. And now we just have to calculate the chi-square statistic. Let's go ahead and do that in Excel. So there's our n, there's our s. Creating the confidence interval, the degrees of freedom have been 9. Blow this up a little bit so you can see it. The variance we take as the square. And now I'm just going to create the numerator by multiplying the degrees of freedom by the variance. That will be then ratioed with these chi-square values. So for the tail, first tail, I'm going to calculate chi-square, since we're looking at the 0.025, and the degrees of freedom, 9. And for the other, I'm going to include the 0.025, but notice I don't have chi-square.inv.rightTail. I'm just using the 0.025. And then I'll take the larger one and divide it in for the lower tail, and the smaller one for the upper here. So I do that, and that, and now I have a confidence interval for the variance. Notice 0 is not in here and nowhere close. That's important to know. That means you have some degree of variation going on. And you can see these numbers match. That's a good way to start this because we calculated the statistic and we calculated with it the confidence interval. Now, if we actually calculate the chi-square statistic, which you really haven't done yet, we take a look at the chi-square by looking at the sample variance and the variance that we're trying to test. We can do a two-tail. It just says it's chi-square. This sigma squared sub 0. Normally that means it's implied 0. But in these cases, that's not going to be 0. That's normally something quite a bit different. So I'm going to take what is assumed to be true, what we find for the sample variance, and multiply by the degrees of freedom. That chi-square statistic will then be turned into a p-value, which is tested. That test, for example, could be something as simple as, let's take a look here. Here's our 3 set. We want to test to see if the variance of something like the metals fund is greater than 625. So I want to test to see if chi-square, in this case, is the variance greater than 625. It's a right-tailed test, which is great because right tail implies we take the alpha and throw it in. So I take my sample variance. Well, we know that 3713 has to be squared since that's the sample variance. We divide by the population variance and multiply by the degrees of freedom. Works out to be 19.85. Let's take a look at this. So all the work that we just saw being done, here are the values. We want to know for this 625, this is a right tail test, sample size of 10. I'll blow this up a little bit for you. We know the sample variance. We calculated the chi-square statistic by ratioing the value of s squared to sigma squared and multiply by the degrees of freedom. And now I'm going to convert this to a p-value. Well, this is interesting because what I'm going to do is take the chi-square dist now, which implies I have a probability I want to calculate, and it's a right tail test. So I'll throw all of my alpha, 5%, into it. So what I'll do is say, hey, I'm going to take my chi-square statistic and the degrees of freedom, and I get a p-value of 0.01885, which is less than that alpha value. So we reject the null, and we find that the variance really is greater than 625. That helps us understand whether or not an impact has occurred. In this case, something may have happened to make this thing go greater than what it would have been because the sample has shown that was ever historically to be true, in this case 625, is no longer true based on this sample. Very interesting that we'd reject this null. Something has changed. Take a look at another one. we'd like to determine whether the variance of returns for income fund differs from 72.25. So is it the same or is it different? 72.25. Here's my S, so I'm going to square it. Ratio the 72.25. Sample size is 10, so the degrees of freedom is 9. And my chi-square is 15. Again, it has to be a positive number. And if I take a look at that, blow this up a little bit. As the problem plays out, sigma squared, now my chi-square test statistic, as we just proved, S squared divided by sigma squared times the degrees of freedom, when converted to a p-value, and what I'm going to do is take the right tail, and I'm going to take the chi-square statistic, 1526, use the degrees of freedom, and get a one-tail p-value. That's a one-tail. This is a two-tail test. So I'm going to double the p-value here so that it works appropriately for two-tail. And when I do, even though this would not be rejected either, I don't reject the null, and I conclude that the variance exhibit what? In this case, there is no difference. Since I can't reject the null, we don't see a difference. What we're seeing here. So we don't reject the null. We conclude that the population standard deviation really is not different. Okay. How do we do two population variances simultaneously? Well, we have to think about is sigma squared 1 is equal to sigma squared 2. Now think about it that way. Sigma squared 1 equal to sigma squared 2, both on the equals or the other side of the equal sign. If I took the sigma squared 2 and divided it from both sides, I would end up with sigma squared 1 over sigma squared 2 on the left or right, and the other side would be a 1. So what I want to do is test if that ratio is really 1. And we'll do it by looking at the corresponding sample variances, S squared 1 and S squared 2. When I ratio two S squareds, two sample variances, that's a distribution called the F distribution. We often refer to it as F, degrees of freedom 1, degrees of freedom 2. Degrees of freedom associated with the first sample variance and the second. They don't have to be the same sample size. Keep that in mind. They do not. So what we'll do is draw from that two sample variances and have their associated degrees of freedom. N sub 1 for the very first sample, minus 1. N sub 2, minus 1 for the second sample's degrees of freedom. Those are vitally important in the calculation of the F statistic. You need to know them, the first and the second, because when we look at the left and the right tail, we're going to have to do a little bit of shifting to make sure it works. You have to keep this in mind as we go through. 1 goes first, 2 goes second to start. So the distribution. It should look a lot like the chi-square distribution. As we look to the right tail, you'll notice we have the F sub alpha, degrees of freedom 1, degrees of freedom 2. So just like the chi-square, we're looking not right to right as we did with the normal. Just like the chi, we're looking from right to left. We have the two sets of degrees of freedom, 1 and 2. Normally we'd use a table to do something, but precision of Excel has vitally improved how we calculate these values. So let's, for example, I have a degrees of freedom 1 of 6 and a degrees of freedom 2 of 8. That means the first sample size was 7, the second was 9. At 5%, we need to figure out what the F statistic would look like. Well, what we would now do is put in the 5%, knowing we're going to look in the right tail. 6 and 8 are my two degrees of freedom, and I get a F statistic of 3.58. Now let's take a look at this. 6, 8, and now I'm going to go ahead and say that 6 and 8 go in. Now that's how I'd calculate it. I could actually reverse this out by saying, let me blow this up a little bit for you. If I want to see this as something backwards, I could throw in the F and take my 2 degrees of freedom, and it returns that p-value which was my initial alpha. So an f calculated would be f dot inv, and we're looking into the right tail. So we had a lot of t, norm, chi, all have inv is a value, dist is the probability. Left tail gets a little complicated. Just to reflect. Degrees of freedom 1, degrees of freedom 2, and alpha is the right tail. Left tail, 1 minus alpha, degrees of freedom 1, degrees of freedom 2. Here it is right here. So it's a lot like the chi-square. However, to calculate it, this is where it gets a little crazy. The actual value is 1 over f of alpha, but I'm flipping my degrees of freedom. So if alpha was 5%, this will be f of 95%, degrees of freedom 1, degrees of freedom 2. It's calculated by saying 1 over f of 5%, degrees of freedom 2, degrees of freedom 1. So if I want that same distribution we looked at, f of 6 and 8, in the right tail it was 5%. In the left tail, 95, that's 1 minus alpha, 6 and 8. But to calculate it, I have to find 5% of 8 and 6. They're reversed. This gives me a value of 4.5, which I have to then find the flip. We have to divide that into 1. So 1 over that flip gives me 0.24. Kind of iffy. Take a moment to look at this. Make sure it makes sense. Let's go over here and look at it. We can calculate what we just saw from the previous page, 3.58. That's 5% with 6 and 8. If I want the value for 95% and 6 and 8, I have to calculate 5% at 8 and 6. So it's a right-tailed test with 8 and 6. Then I simply ratio it, and I get that value. Again, the p-value can be easily calculated backwards, as we just saw, 0.5, and I could do the same thing to calculate 95 right here by taking and creating a p-value and looking at this to say, how would I like to see this? 95%. This will go a long way as we calculate confidence intervals for our F statistics. So just take a look at this for a moment. So we just saw how we would do this in and out. How do we calculate the confidence interval for this F, which is the ratio of the two variances? Well, what I'm going to do, there's your F statistic, F alpha over 2, degrees of freedom 1, degrees of freedom 2, F alpha over 2, degrees of freedom 2, degrees of freedom 1. So it's 1 over. I'm flipping them back. This one, remember, is a 1 over value. Pretty interesting. So now I'm going to take the ratio of my two sample variances and just flow through with a calculation, realizing my degrees of freedom minus 1, minus 2. Here's a sample. Let's take a look at an Excel. It probably makes a lot more sense for us over here. I'd like to figure out what a confidence interval would look like for this, a 95% confidence interval. So to start, here's my alpha, 5%. Degrees of freedom, well, the sample size for the first is 11 and its sample variance is 182.25. For section 2, sample size is 16 and has a sample variance of 457.96. So the degrees of freedom, the first is 10, 11 minus 1. The second is 15, 16 minus 1. And now what I'm going to do is I'm going to calculate those F statistics as we saw before, where I just flip-flop the degrees of freedom. So from this, I'm going to pull in 0.025, and I'm going to take 10 and then 15, natural order. For the second, I'm going to do the same thing, but I'm going to take the 15 first. The reason is, here 15 must go before 10, here 10 goes before 15. Now all I have to do is take the ratio of the sample variances and fill out the equation. So just to be clear, let's make sure we pull these numbers over here appropriately so you can see them. little big, but I think that makes sense. And what I'm going to do is do a simple calculation. I'm going to take the ratio of the two, and I'm going to multiply by 1 over the first, as we see here. Then I'm going to do the same thing for the second using the formula, their ratio, and then multiply by 3.52. That gives me the confidence interval for in this case, the 95% confidence interval for the ratio of the population variances. Remember, we're looking for a value about 1. Remember, that's the goal, is if they're the same, 1 should be in there. In this case, between 0.13 and 1.4, 1 is in there. Make sense? I hope so. To the end, hypothesis testing. This is what we ended for. To get to this, the ratio of the two-tailed test, are you equal to 1 or not? Is a ratio test a right-tailed test, meaning the ratio is greater than 1, or a left-tailed test? The ratio is less than 1. And the F statistic will be initially calculated and computed by taking the sample variance ratios. Simple enough. Well, let's just revisit what we saw. We want to determine whether or not the variances differ. Well, we just calculated this confidence interval. 1's in there, so we can't reject that null. 1's in there, so yeah, they're determined to be the same. We can't prove that they're not significantly different. Great. One-tailed test, let's try a little different one. We specify one tail as right tail, and what we try to do every time is put the larger sample variance in the numerator, and that forces us to view it as a right. We don't do critical values, but critical values, if you're a critical value person, I know some people may want to be, that is actually easier to find them doing it that way. But let's do something like this. We want to know if metals involves more risk than income. Now with that, risk will say, risk being one has more variance than the other. So is the variance, this squared, greater than this? If that's the case, their ratio would be greater than 1. Else, we wouldn't reject the null. We say we can't prove that it's greater. So we can't prove that it has more risk. So for this problem, we have a whole bunch of data. Both are equal sample size, both at 10. The sample variance for the first is 3713. We've seen that before. The other is 11.07. I believe we've seen that. We can actually square each and get a statistic. That's 11.25. Pretty simple math. If you want to calculate a critical value, great. You could do that. You could calculate what the value is critically. You know what the value is by using the inv value. You can compare one to the other, and the value would be rejected. Now, if we look at it the way we've done it up to this point, this was step 1, problem we were just looking at. Here's what we just proved. Here is our statistic. I'm going to square metals over squared income. But now what I'm going to do, let me blow this up a little bit again so you can see it. Sometimes Excel kind of backs down. In this case, I'm going to do fdist, because we want to find a p-value. And I want to do a right-tailed test. This is pointing to the right, and both have 9 degrees of freedom. That p-value is less than alpha, so we reject the null. And in the end, by rejecting the null, as we do here, to the original question, does the metal fund involve more risk? You just proved from this sample that it does. Now, there is one more thing. Excel has this add-in with a descriptive statistics tool that we can use for an F-test. And F-tests are great if you want to see one. We can do something called an F-test to sample for variance, which is a great test for something like this, which we just saw. Remember, we're ratioing them to get to 1. Here's something you could do. Say we have 2 bus services, and you're trying to see if the school district will renew the bus service contract for Their competing brands are Millbank and Gulf Park. Whichever one has the lower variance of pickup is the primary point of service quality. If the variances are equal, price is the deciding factor. So ultimately, if they're equal, price is the most important, but if you can show that one is less than the other, you'll pick the one that has less variation because the arrival times are so important, especially if you're a parent and you're waiting out for kids. You know how important that is. 5 minutes here, 20 minutes there. So you take a look at 26 arrival times from Millbank, and they have a sample variance of 48, and a sample of 16 from Gulf Park, and they have a sample variance of 20. Can you, at 90% confidence, which is an alpha of 10%, help them out? Well, I have all the data. Here's all the data. Notice sample sizes don't have to be the same. You can run data analysis. It'll pop up. F-test to sample for variance. Millbank. We'll calculate all of them. We'll do the same thing for Gulf Park. We had labels. I'm testing this at, say, 10%. I'm just going to put it somewhere over here. Put it over here somewhere. If I hit OK, what you'll get is a pop-up just like we saw, and you'll get this. I'm not going to do it because it'll duplicate the effort, but you'll get this. And you get a one-tailed p-value of 0.04. Now this is a two-tailed test, remember? So I have to double that p-value. It doesn't do it for you here. So that doubling still leaves me below 10%. I reject the null. I find that the variances aren't equal, so they're not going to decide on price, they're going to decide on variance. And oh, by the way, if you look at the variance of Gulf Park, it is lower than the variance of Millbank. I may then want to do a separate test with a separate sample to test that Gulf Park truly is less variance. F-test is one other way to do it. You can see it's a different kind of call. You pull it in, you get very similar results. Just putting that out there if you move forward and do more in statistics. So that's what we do in Chapter 11. Next comes Chapter 12, and then we'll move into ANOVA and regression all the way through to the end.